can look at the surface of polymer, or even solid, like a quartz. You can do the surface phonons. And we can look at the surface of neat liquids. We can study catalytic reactions in ambient conditions, not in vacuum chamber. Okay? And we can do surface dynamics with time resolution of femtosecond and surface microscopy. Okay? So just give you some example. We talk about polymers, for example. You can see that, of course, in many applications, you would like to have the rigidity of the bulk because the polymer is supporting something. But in many applications, you would like to have the surface of polymers with specific characteristics. For example, if you want to replace some part of your body with polymer, then that polymer has to be so-called biocompatible. It has to be compatible to your blood and other things. So it's important to design surface of polymers with particular characteristic or structure. But the chemists are very smart. They know how to do it. They can say, I put this in, and then something will come to the surface, and so on. The problem is they don't have any tool to know what has actually coming out to the surface. Okay? If you use X-ray, you use X-ray, maybe you can see few layers, so you can get some information. But all the other methods are just not surface specific enough. Okay? So here is a case for us to use the some frequency spectroscopy to detect the surface layer of the polymer and figure out what the structure is or what species are at the surface. So, for example, I have a big biopolymer like this. Okay? You can see, the chain is long. I have 3 different polymers. The only difference is the end group is different. One has this end group is just hydrogen. The other has this PDMS. The other has PEG. Okay? And you know that if you try to do infrared Raman spectroscopy, these 3 will look exactly the same because these species at the end is too small. And indeed, you see that infrared spectra of the 3 look the same. But if you look at some frequency spectra, they actually are different. Some PDMS only, without this long chain, has this particular spectrum. But then this biospin S with PDMS at the end actually shows this PDMS appearing at the surface. And so it's also true for BN and so on. But anyway, I just quickly say that the spectra are different. And you can see why they are different. And water is another case. We know water is extremely important, but not in Brazil. Okay. But in the third world country, the water is going to be causing disaster much earlier than the energy problems. I mean, millions of people will die in after 20 years. This is according to the UN survey. So many, unfortunately, all the rich countries do not have this problem. But anyway, we're still interested in how to economically purify the water. And that requires, for example, the filtering, and that's the water interaction with surfaces. And those are the important issues. And with the some frequency spectrum, we can actually look at the surface structure of water interface. And that is the only way to get a vibrational spectrum of the water interface. And from the spectrum, especially the imaginary part of chi, this is an example of what I said, that phase information is important. With the phase information, I can get the so-called imaginary part of the susceptibility, and that directly related to the resonance. If it's positive, it indicates OH is pointing up. If it's negative, OH is pointing down. And so from this, you can see there's a part of the species with OH pointing up, part of species pointing down, and that is the dangling OH bond on the surface. Okay. So knowing the structure, then you can really understand how the interface structure could change when you perturb it in a certain way, or it interacts with something. And so this is just explanation how I understand the spectrum. Okay? And here I just want to show you one interesting case. If I have the vapor water, usually that's considered as hydrophobic, because the OH dangling bond is sticking out, not interacting with anything above. On the other hand, if it's hydrophilic, then this OH bond is being grabbed by the other side. And this, for example, is the quartz water, the quartz water here, hydrophilic. Okay? On the other hand, this is hydrophobic with solid on the other side. It could be the hydrocarbon chains. And you can see the three spectra are very different. Right? They're all water interface. Three different water interfaces are very different. Although this is hydrophobic, this is hydrophobic. And why are they different? Well, part of these are due to charges at the interface. When you have quartz water, quartz can be ionized in water. It has a pK value, or the equilibrium value, of 3, roughly. So at the normal pH equal to 7, it's actually charged. And when it's charged, the field is, well, anyway, there's a surface field coming from the charges, and therefore reorient the water molecules with OH pointing up, pointing towards the interface. So that's why it has a larger positive value. And so you wonder why this is more positive. Well, indeed, this is also because of charges at the interface that reorient the water molecules, making OH pointing towards the interface. And this is interesting, especially for Sid. Look at this one, okay? If I have charges at the interface, then the negative part becomes more positive because there's a surface field pointing up like that, reorient the OH pointing this way. So it's up. This is when I have iodine at the interface. Now with OTS, the hydrocarbon chains, in pure water, it's even larger. So it indicates that there is negative charges absorbed at the interface with the hydrocarbon chain. And to prove that, you see if I increase the pH so that I have more and more OH minus in the solution, then you see the OH minus gets absorbed onto the interface more and more. So this is why I said that maybe in your case, when you have the colloidal particles with hydrocarbon chains on it, they will separate because of the charge-charge repulsion. Okay. Okay, so the general comment is we still have many, many problems that we can do, and especially for biological interfaces. But I could do all other problems, but I don't dare to touch biological surfaces. I cannot even remember the names.
Ok, mais alguma pergunta? Nenhuma pergunta mais, tem certeza? Okay, so let's thank the
Thank you
speaker
very
again.
much. Thank you. Thank you.
Bom, então é isso aí. Até amanhã. Boa noite aí para todo mundo.